Hi everyone. Today's topic is dynamic programming, and with this concept, we would typically take previous subproblems to our advantage to compute our current problem's solution. And so we would also store it in some kind of other structure very similar to our given input. And then dynamic programming also reduces a lot of complexity and time compared to recursion, since recursion sometimes computes or recomputes different data unnecessarily, which dynamic programming helps reduce. And so we can just take a look at a LeetCode problem so that you get a better understanding of how to use dynamic programming and breaking a problem into even smaller problems and then building our way up from there to get the solution to our current problem. And so let's look at an example. So the problem is given an n by n grid filled with non-negative numbers. Find a path from the top left to the bottom right, which minimizes the sum of all numbers along its path. And a note is that you can only either move down or right at any point in time. So given looking at the input that they gave us, we have this 2D array, and starting, we need to find the minimal path sum from this top left cell to this bottom left cell, bottom right cell. And so the minimal path sum is going to be from 1, 2, 3 to 1, 2, 1, 2, 1, which is a sum of 7, and that's the smallest path sum compared to all of the other valid paths to 1. So compared to this path, or any other path, this is going to be the smallest one. And so we can take the idea for dynamic programming and storing the subproblems to help build for our current problem. And what we can do is take the minimal path sum for our previous cells, store them to compute the next cell's minimal path sum. So let's take a look at our solution, and what we first want to do is create another 2D array of the same size, so same amount of rows and same amount of columns as our original grid or input. And so taking a look or drawing out our original input that they gave us, we can just create another 2D array of the same size. And so the next step is to initialize our first row and our first column. And the reason for this is because the only way to reach any cell in, say, our first row is to traverse this path. You cannot go down and then to the right and then back up to the cell, because our problem specified that we can only move down or right at any point in time. And so what we can do, say for the first row, is just add up all of the path sums along the path to reach our current cell in our first row. So let's take this input for example. We're going to have 1 obviously in the first cell because that's the minimal path sum to itself. And then to reach 3, we're going to have to go from 1 to 3, and adding those two numbers together, we get 4. And so now we have the minimal path sum to our cell 3, which is going to be 4. And so for our next cell over here, which is going to be 1, we can take the minimal path sum of our previous cell, which is 4, and then add it to our current value. So it's going to be 4 plus 1, which gives us 5. And the same thing we do for the first column on the same process. From 1 to this cell right here, the minimal path sum is going to be 1 plus 1, which is 2. And then using this minimal path sum to this cell right here, which is 1, we can add the minimal path sum from this cell to our current cell. So 2 plus 4, which is 6. And so now that first part is done, we just did this entire part. We can start on actually filling the rest of our cells. And so we can start from this cell right here, which is why we start at row 1 and column 1. And then the value of this cell will depend on the minimal MinPathSum above it and the one to the left of it, because that's the only way you can reach the cell from this point. So you can either move down or to the right from here. You can't move diagonally or from 5 to this cell or any other way. And so that's why we can find or use the minimal of the MinPathSum to this cell versus this cell, and then add it to our current cell's value. So in our case, it's going to be 3, oh sorry, not 3, 2 plus 5, which is our current cell value, which is 7. So 7, or we have 4 plus 5, which is 9. And so the minimal of that is going to be 7. So this is our current cell's minimal MinPathSum. And so now we iterate to the next cell and do the same process. So we can look at the top cell and the bottom left cell, or sorry, not the bottom left cell, the most direct left cell, and see which is going to be the smaller sum. So 5 plus the current value of the cell, which is 1, or 7 plus 1. So it's either 6 or 8. And obviously 6 is smaller than 8, so this is going to be our new minimal MinPathSum. And we can just repeat this process for the next cells. So 7 plus 2, which is 9, versus 2 plus, sorry, not 2, 6 plus 2, which is 8. And so since 8 is smaller than 9, this is our new minimal MinPathSum. And so our last cell, we can see either 6 plus 1 versus 8 plus 1. So that would be 7 versus 9. And obviously 7 is smaller than 9. So our minimal MinPathSum from this top left corner to the bottom right corner is going to be 7. And we already confirmed that since we went through this entire path over here. Then finally, we just want to return the last cell, which is denoted by the array specified by index rows -1 and columns -1. And this will give us our solution. So the minimal MinPathSum from starting from the top left corner to our bottom right corner.